Good afternoon. If you don't mind putting on your headsets, we're going to watch the premiere of Avatar 3, or actually, we'll be having a session today, CMP302, about accelerating engineering using HPC on AWS across industries. So before we get started, I want to remind you that towards the end of the presentation, you will have QR codes on the screen, and I encourage you to go take a picture. They will give you all the sessions that will be covering HPC throughout reInvent this year, and will motivate you to go and attend them. The second thing that I wanted to say is we really appreciate everybody filling out the surveys at the end. That is how we can get better year on year and give you the best content and the best experience when you come back next year at reInvent 2026. So before we dive into the presentation, I wanted to introduce two additional speakers that will be on stage with me a little bit later in this hour. They're sitting up here up front. The first co-speaker is Karima Dridi from ARM. She is the productivity engineering, Vice President of Productivity Engineering at ARM. She leads global teams that run ARM's large-scale design and verification flows, including adopting AI and cloud-based EDA to help ARM's CPU and Neoverse platforms reach customers faster. She will be the first speaker to come on stage after my 20-minute discussion. The second speaker that will join me, her name is Taylor Gowan. She is the modeling and engineering team lead at DTN for atmospheric science. She leads a team of scientists who build AI-based and physical-based numerical weather prediction systems on AWS, powering DTN's global forecasts and weather intelligence for customers around the world. So today's topic is accelerating engineering cross-industry HPC cloud transformations. Let's take a look at the agenda. I'm going to start by giving you some key market trend updates. And if you attended Supercompute in St. Louis 2 weeks ago, there will be a repeat of what you heard through the Hyperion Research discussions. I'll dive into cloud adoption in HPC. We'll talk about the AWS HPC building blocks. We'll talk about cross-industry use cases to make all of this a little bit more real. And Karima and Taylor will talk about the journey of ARM and the journey of DTN as they were leveraging AWS for their HPC needs. I'll give you a few comments at the end for recap and remarks, and we should be able to close within an hour. So let's start with a few market trends. As you can imagine, HPC and AI as an overall market is growing quite a bit. The numbers that you see is the growth in 2024, according to Hyperion Research, was 23.5%. Historically, over the last 20 years, growth rates were about 7 to 8% a year. So about 3 times the growth rate we saw last year in 2024. And the overall market size for HPC is now close to $60 billion. And just a little spoiler alert, cloud is about $10 billion out of those $60 billion. And you may think, well, of course, last year AI grew gangbusters, so really that's the effect of AI. And you're not completely wrong. But what I do want to point out is that if we take out AI as part of the growth of the HPC and AI market, you still see that the HPC portion, traditional simulation, calculation, scientific innovation, still grew 8.4%. And when we look at that growth compared to historical growth of 6 to 8%, that's still faster than we've seen in the past. So compounded, HPC traditional workloads and the AI enhancements that we all see and implement in our day-to-day, this has been driving this growth of over 20% year on year. The AI infrastructure is fantastic. As I said, that portion of the growth was 166%. So now let's double click into the cloud adoption, because we're here to talk about cloud, right? So cloud adoption in 2024, I said, is about $10 billion, and we expect that adoption to continue growing. And if you look at the prediction for 2029, belief is that it will be as high as $23.7 billion. Which will account for about 20% of the overall HPC and AI market. So now if you do the math, If it was 15% last year and it's going to be 20% of the overall market, that means that cloud is growing faster than on-premise. Not really a surprise, and we'll talk about the reason for which we see that trend, but something to note. Here are 5 reasons that explain why cloud is growing faster than on-premise. Number 1 reason, some workloads cannot run on-premise. The jobs are blocked, capacity limits, and you want to run a simulation, you want to design a part for a car, or you want to go after the next scientific discovery, but the queue is clogged and you can't run it on-premise. So cloud can really help in that situation. The second reason is access to the latest GPUs. If you watched or attended the keynote with Matt Garman, our CEO, you saw that we are already launching GB300. We're launching Trainium 3. We have Trainium 4 being announced already. That's going to be launched later. All those technologies are moving fast, and in the cloud you have access to them as soon as they're available. You don't have to go build a data center, allocate power, and try to bring all this to bear in a record time. Number 3 is run at larger scale. We all think we design the right environment, the right infrastructure for what we need today. We put a little bit buffer for tomorrow and the day after tomorrow, but we always end up in a situation where we need more. More infrastructure, more access to technology helps you design or build more products for your customers. And cloud elasticity is what makes it possible. If you decided to use X instances and tomorrow you want twice or 10 times the number of instances that you were using yesterday, you can do that in a cloud environment. Number 4, time to results and queue times can be shortened. It's just a lever. You want bigger infrastructure, you can get things done faster. You may have to pay a little bit more, but at least you have that flexibility. If you have a looming deadline to go finish a design and you need to go pile it up high so you finish on time, you can make it happen in a cloud environment. The last one is collaboration, globally, and sustainability. I encourage you to go on the AWS website. There is a page that talks about our efficiency for our data centers. PUE, amazing. Considering the scale that we're at, and then collaboration globally. Anybody in the world can access AWS instances, and if you have your data in an AWS environment, everybody technically under your account can have access to it. So if I had to summarize it in one diagram, this is the diagram. On the left, you have a wheel, multiple sets to go from the idea to the data. On the right, with cloud and HPC being run in the cloud, you can go a lot faster. 4 steps, you go from an idea, and before you know, you already have the results. You can analyze, and that's the flexibility and the power of cloud. So let's dive a bit into the building blocks on AWS. We have built purpose-built building blocks for HPC. You see them here in 3 sections, from the bottom to the top. At the bottom, you have the infrastructure components. HPC optimized compute instances, HPC optimized accelerators, HPC optimized network fabric, HPC optimized storage. You have access to that. Then you get to the next layer is how do you consume. You can consume on demand. You can create savings plans if you want to commit to a longer term utilization. You can have access to spot instances. And then recently, we also launched capacity blocks. Is you plan in the future to use that capacity and we reserve it for you. On top of that, we've got a set of services, and I'll point out 4 of them. PCS, ParallelCluster Computing Service, Batch, ParallelCluster, and RES, Research and Engineering Studio. Those are 4 services that are available as soon as you build up your environment. And those services help you build and manage your environment for all of you HPC users. Let's dive shortly into the instances that are optimized for HPC. On the compute side, you have HPC 6A, 7A, 6ID, 7G. A little bit of a cheat sheet. The number is the generation. So 6 is 2 generations ago, 7 is current, 8 is the one that just came out and that will come out. The letter at the end is the technology. A stands for AMD, I for Intel, and then G for Graviton. On the right-hand side, you see all the accelerated computing technologies that we have from NVIDIA, from the L4 all the way to the GB200. And again, if you heard the keynote with Matt Garman this morning, GB300 being launched already. Now, this is just for HPC today. I do have one slide letting you know that pretty soon, cannot tell you when, but pretty soon in 2026, we will have an HPC 8A, which will be Turin-based, which is the 5th generation AMD EPYC processor that will be available to all of you. Get excited because it's better performance, cost performance is going to get you into the next tranche of workloads and your ability to save and go faster for your simulation and designs. Okay, let's take a look at the rest. Those were optimized for HPC, but now we also have a broad portfolio. And the portfolio here, I'm not going to go through every single instance, you can find them online. But I do want to point out that we also at AWS design our own chips. Graviton is our processor based on ARM. Trainium and Inferentia are accelerators. And Trainium sounds like a training chip, but it's also great for inferencing. So you have those chips here that are available, and you can have access to them. If I do a double click into Trainium, you may or may not know that we have made a decision to build a massive set of data centers under a project called Rainier that will host 500,000 Trainium 3 chips that will be Trainium 2 chips, sorry, that will be used to train the next generation of Anthropic Claude model. So if you in your mind you were thinking, well, Trainium seems to be an interesting silicon, does it really scale? We're about to demonstrate to the world that yes, it does scale and it does bring the next generation of large language model to life. Graviton 4, I'd be remiss not to mention that we've continued to innovate out of our 4th generation of Graviton chip. Based on the Neoverse ARM core, a lot of cache, 7 chiplets, 12 DDR5 channels, and 96 lanes of PCIe Gen 5. Okay, so compute is great. Compute without storage is useless. So if you go into your environment, you now have all the compute flexibility that you want, but in storage, you have object, file, and block. Object is S3, which is the most popular, lowest cost solution for all of our customers. But when you get into the file type of portfolio items, we have EFS, FSX for Windows, FSX for NetApp on tap, FSX for Lustre, which is probably the most commonly used high-speed storage solution for most of HPC customers and AI customers, and then FSX OpenZFS. And then if you're block, then you have Amazon EBS. But all those are connected through our EFA fabric to those compute instances, and you can mix and match, and you can do also some clever movement of data between object and file, depending on what you're looking to accomplish in your environment. So if you remember the layer cake that I showed you, you have the 3 layers. You have the infrastructure, you have the consumption model, we talked about storage. Now you have the orchestration layer on top. And I'll only talk about 3, I know there were 4 on the previous slide, but I'll talk about PCS, batch, and ParallelCluster. PCS is a fully managed service based on Slurm and makes it easy and more intuitive to go build your environment. If you don't want to go all CLI and build it yourself, or if you have teams that you're managing that don't have the in-depth knowledge, the environment is already preset. And encourage you to try it. We launched it about 1.5 years ago, and we're at a point where it's fully featured with all the improvements that we've gotten through the initial customers. Second one is batch. Batch is a computing service that schedules and runs containerized workloads. It has a full range of compute offering and could be the right solution for you if you're running containers. The last one is ParallelCluster. That's our legacy service, and legacy doesn't mean that it's not still going to be very much used by a lot of you. It's open source, and it's what most of our customers are using for HPC. I would be remiss not to talk about quantum, and this may seem weird because this is not a quantum talk, but we see more and more HPC partners, customers, researchers think about quantum. And at AWS, we have made an effort to continue to bring technology to our customers and partners. And we have this service called Bracket that uses a lot of our partners' quantum computers and makes them available to our AWS customers. So now in one single environment in your AWS account, you can have access to HPC environments, but also quantum environments, and you can do mix and match. And by the way, the world is still trying to figure out where to fit quantum in an overall workflow. But today we're looking at least 3 modalities that we have made available: ion trap, supercomputing, and neutral atoms. If you're interested as an HPC customer, you even have access to credits to go run some quantum experiments. And feel free to talk to me after the presentation today if you want to know a little bit more about it. Okay, I'm going to go a little bit faster through the rest of the slides because I want my co-speakers to also have plenty of time to talk about their journey. But all this technology is great. It's theory, it's out there, you can click it, but a lot of customers and partners have used that in the industry. And I'm going to go one after the other. The first one I'm going to talk about is CAE and EDA for structural analysis, finite element analysis, IC design, timing and signal integrity. You recognize a lot of the logos at the bottom. The second area or industry where we've seen a lot of utilization of AWS for an HPC framework is healthcare life science. Genomic sequencing, drug discovery, personalized medicine, epidemiological modeling. That's a tongue twister. But the names at the bottom, you recognize the majority of them. And they're using AWS for their HPC workloads in HCLS. Energy, power grid simulation, nuclear reaction design, oil and gas, renewable energy system modeling, all those logos that you recognize. The next one is financial services. A lot of the financial services platforms are running on AWS. And so for an HPC workload, risk analysis, fraud detection, portfolio optimization, market simulation, and forecasting, all those are being used. Auto, computer fluid dynamics, crash and safety, advanced driver assistance, autonomous driving algorithms, all those logos that you recognize. And the last one is university and academia, where you see high energy physics, astrophysical modeling, computational chemistry, social science, and analytics. Actually, I missed one. I shouldn't have missed that one. Weather. Global climate modeling, weather forecasting, hurricane and storm surge, air quality modeling. And recognize the DTN logo in there. Okay, as a slight primer for our next 2 speakers, I'm just going to cover briefly some of the challenges that are being resolved in a cloud environment for EDA. I'm going to skip this and just go to the challenges themselves. Why would EDA run best on AWS? It gives you the ability to innovate faster, collaborate faster and better, reduce risk, and reduce cost. Weather. Giving you, again, just a little primer as to why you would want to run weather modeling on AWS in the cloud. Look at these benefits. Deploying production weather and climate forecasting faster, collaborating better, reducing risk, and reducing cost. So you can see a theme here. You can do a whole lot in the cloud on AWS. But this, again, is only theory names. So it is my pleasure to bring Karima to the stage so she can walk us through her journey at ARM, accelerating engineering on AWS.
Hello, everyone. My name is Karima Dridi. I'm very excited to be on stage today. I'm leading productivity engineering in ARM, and my team is looking after compute strategy and enablement for engineering. Today, I will take you into ARM cloud journey, a transformation that is shaping our business and our industry. I will speak first about ARM business, then I will take you through ARM cloud journey, how we use cloud to build our product, and last but not least, I will speak about the optimization and efficiency happening in our, to enable best usage of cloud. So first of all, ARM global compute footprint is unmatched, powering nearly every connected device and enabling innovation across industries. 100% of the connected global population relies on ARM, and over 325 billion ARM-based chips have been shipped up to date by our ecosystem. We also have 22 million software developers on ARM. So ARM has definitely the scale, the power, efficiency, and the performance that enable to accelerate AI everywhere. In fact, on the infrastructure side, we've come a long way since the launch of our Neoverse brand 7 years ago for cloud and data centers. We have shipped over 1 billion Neoverse core into data centers and currently are tracking towards 50% unit shipment into the hyperscaler in 2025. And we owe this success to the technology leadership as well as the strength of our ecosystem, including AWS. We also, working together, we have enabled 70,000 companies to adopt ARM in the cloud. 15 years ago, it was mainly ARM building and supporting to move software to ARM and making investment in the infrastructure space. Today, all our ecosystem, all hyperscalers are actively investing to ensure ARM supported. The question is not anymore, does it support ARM, but mainly is it supporting ARM first and delivering seamless user and developer experience. ARM and AWS strategic partnership started back in 2018. It is about a shared vision that is fueled by the efficient and scalable compute, as well as a joint value proposition with the Neoverse and Graviton. Okay. So now I will speak about ARM and how we are using cloud actually into our environment to build a product. As we look at our current industry pressure, as we look at our current business landscape, we have 4 interconnect challenges that are feeding directly into our strategy and priorities. The first one is the industry pressure driven by increased complexity, the relentless time to market, and the industry dynamics. This is shaping how we plan, execute, and deliver our technology. The second one is the explosion for compute. We saw compute, and this is driven by AI workloads and also the need for sustainability. We saw definitely a shift from compute being a cost center to compute being a strategic enabler, one that must be power efficient and high performance. A third element, which is the strategic goals across our industry. Our business units have their own priorities, yet the shared common goals across scalable compute, the speed of innovation, and the need for transformation. Last but not least, that transformation, to be able to move, we need to have adopt cloud agility into everything we are doing. So our strategy is about bringing these four parts of the puzzle into one cohesive forward-looking plan. Our product development cycle can take at least a year or so, and this is based on the complexity and scope of product. It is split into 2 main phases, front-end and back-end, and each of these phases has different needs in terms of compute and storage. Front-end is about massive regression, a smaller memory file, single-threaded, while back-end is about much longer jobs requiring significant memory, and it is multi-threaded. So we are leveraging on different type of instances there from AWS. So workload placement is critical to enable faster iteration of project and efficiency, and right-sizing instances to fit this workload need is as important. So cloud agility, in summary, is a cornerstone in our ARM strategy and product development. But it is not only about workload placement. The cloud-native approach mandates us to tune our infrastructure to unlock the full potential of computing there. So we build platforms that enable to run different jobs and leverage on the power of cloud. These platforms were built with the 4 elements taken into account. The first one is fit-in-purpose platform, which is about the right platform with the right job with efficient data and storage management. Automation plays a crucial role into complexity management. The goal is to increase reliability, reduce costs, and remove human bottleneck. Third is observability. It is providing real-time insights for failure analysis, cost control, but also any fault tolerance there. The goal is really to keep the resource usage optimal. Last but not least, the continuous integration, continuous delivery, which is about streamline application development and release features fast and reliably. So in summary, it is not only where the apps are running, but how they are optimized and built that unlock the full potential of computing. So I will zoom now on 2 platforms that we build with the cloud-native approach. The first one is Cloud Runner. Cloud Runner is optimized for front-end jobs mainly. Cloud Runner is operating really as a factory. It is leveraging on AWS batch scheduler. So ARM and AWS worked hand in hand to improve the cloud, that AWS batch into the leading service it is today. So Cloud Runner in few numbers so we have 500K concurrent job running in parallel, 100 projects executing, 1,000 engineers working on those projects. The environment can be ready within 1 hour, and we can support security and export control technology. So this is on top, is leveraging on Spot, which is benefiting of 90% saving plans because this job can be interrupted. And we also leverage on 70% cost reduction in terms of storage, as these jobs actually are running without any they don't require shared memory. So this is what a factory means in terms of front end, and it is enabling us to increase productivity of engineering. So Cloud Foundation Platform, which is our CFP, it is optimized for back-end jobs, and it is redefining how we see CFP as another, by making its functionality completely equivalent to another HPC. It is using LSF as a scheduler and FS6 NetApp on top as a storage system. So this is operating exactly like on-prem. Your user identification is using the LDAP system. We can have accesses using Unix permission. We also, from user can connect to on-prem to run to access Get repository, but also we can run in batch or interactive using GUI command or interactive line. The main difference here is the elasticity of the cloud, as we no longer need, we no longer need to reserve from day one 100, for instance, terabytes of storage. We can start by 5 terabytes and then scale up as needed. So this is a hybrid environment that enables us to benefit from security and performance of HPC combined with the elasticity and the performance of the cloud. So AWS Cloud help providing flexibility needed to run our job. It's provide both compute and vCPU peak. It's enabled to address vCPU peak as well as the storage capacity. It is not only technology shift, it is a transformation how we build, deliver, and execute. our projects. The number of projects we run now in parallel shifted our industry from CPU limited to human limited. So we can see there that we could have 4,000 slots on-prem for 4 months. Now we can have 5 times that within 1 month. So this is a good example for front-end verification where we can see the elasticity of the cloud. We can scale up to burst to our peak, then scale down to reduce costs. We also see that we can benefit from up to 66% of added throughput once we move to the cloud. We saw that number of projects that we can run in parallel now, we can build actually in the space of 4 years, moved from 15 products to 25 products as of today. Okay, I spoke about the cloud agility and how it is a cornerstone in why we are building our products. But the optimization part is critical here. Cloud using the resources in most efficient way is as important. So I will zoom about 3 areas, which are the saving plans, the tooling side, and also the storage side. AWS offer different saving plan to enable to save costs for the product we are building. So Spot can be used as a way as a type of instances for interruptible jobs. Saving plans like instance saving plan is mainly about predictable jobs, and compute saving plans is mainly for evolving type of jobs. This is an example how we can stack up this saving model by starting by saving plans, then completing on demand for securing the slot, and then move any job that can be interrupted to Spot. That's very important, and this is how we do it on ARM. We can see that we are using a mix and balance type of saving plan. It is very important to monitor how we are using this slot. This is an example of one region where it is Oregon. We saw that we are basically having the on-demand capacity massively increasing, but no coverage with ASP. So we decided to move some of the jobs on ASP to save costs. And this is important. It is all about timely decisions that we make in this space to enable efficiency and to run the jobs in most optimal way. EDA, electronic design automation, my colleagues spoke about it. They are critical for our development, yet they can have different behaviors and different needs, and that can impact directly the performance of job we are running, even for the same IP. So it is very important to look at the characteristic like runtime as well as kernel tuning to enable best usage of this EDA tooling, and can be some other tools on your side. So understanding how these tools react is very important to optimize both cost and runtime. As we can see there, this is for front-end jobs. And the breadth of choice that EC2 instances AWS providing is there. So it is critical to adapt the tooling to the right instances here. The workload can be very spiky, and the read-write performance can vary dynamically. So it is important here as well to monitor the usage, how this workload reacts. Mainly for EDA workload, they can have different characteristics again. Front-end can be limited by metadata, AUPS, while backend activity can be limited by data throughput. So it is important to have that elasticity for the storage system. And FS6 NetApp is enabling that scalability, and it is providing very compelling results when it comes to EDA type of workload and the storage system that go with it. Graviton impacts of front-end. Graviton can have we can see that it is very performant in terms of dollar, and also performance runtime. we can see how it is overperforming versus AMD and Intel. This is comparing actually Graviton 3 and 4 versus other provider. So it is definitely very critical mainly for our front-end verification, where it is providing this great result. In summary, cloud-native approach is really critical and enabling us to deliver products in most efficient way. Efficiency, looking at efficiency is very important. Profiling and benchmarking of the tooling play a crucial role in how we manage that complexity and also optimize cost and runtime. And Graviton instances is really providing very compelling and advantage for our environments and our run. So our cloud journey started back before 2020. It is work in progress. We need to reinvent the way we are doing, and we are optimizing our resources there to unlock the full potential of computing. Thank you.
All right, I'm Taylor Gowan. I am the team lead of the Atmospheric and Modeling Engineering Group at DTN. At DTN, our mission is to provide decision-grade weather intelligence data to our customers that have a material business risk. This includes agriculture, aviation, utilities, energy trading, offshore, and so much more. So today I'm going to tell you a story about how DTN went from an on-prem computing company to a fully cloud-based system driven by HPC at AWS. We're also going to talk about how our forecast system is fully integrated within HPC and how we're pushing the boundaries of numerical weather prediction with the advent of AI and NWP, and we're doing that in production in AWS. So I kind of wanted to get a pulse check before we get on to the presentation. How many of you, if you show of hands, are familiar with numerical weather prediction? Okay, now how many of you have a weather app on your phone? Okay, so that's everyone. Okay, so that's output from a numerical weather prediction model. So whether you knew it or not, you are all familiar with numerical weather prediction. What a lot of you probably don't know is that increases in skill in numerical weather prediction have been directly tied to increases in skill and efficiency in HPC. With every new iteration of HPC, we're able to increase our computational power. This is allowing us to move from global coarse resolution forecast models to convection permitting scales and sub-kilometer forecasts. We're able to assimilate more high-quality observations. These are billions of observations from things like satellites, aircrafts, buoys, covering the globe in places where we don't have traditional observations available. And then finally, of course, it is giving us a better understanding of our atmosphere. So we're getting better physical parameterizations, we're getting better data assimilation, and we're understanding the processes that drive our weather every day. So as I said, I'm going to be telling you the story of my company and how we are using HPC and AWS. We're going to talk about where we've been, where we're going, and where we are right now. So for many decades, we were using fully on-prem HPC. This worked for us for a while, but then we needed the scaling and elasticity that HPC and AWS provides for us. So in 2020, we completed our migration to AWS HPC for both our atmospheric and marine modeling workloads. In 2022, we were starting to push the boundaries of our price and performance with optimized HPC for specialized modeling, which we'll talk about more a little bit later. In 2023, we moved to driving our entire DTN forecast system with AWS HPC. And then just this year, in 2025, we started running production AI and NWP models in the cloud. And then looking forward to what we've got in the future, we're certainly going to be looking at new AWS offerings such as Parallel Computing Service and the new HPC 8A. So some of the building blocks for our main workloads, for the specialized modeling, we use ParallelCluster to run instances like HPC 6 and 7A. We use FSX for Lustre for our file I/O, and then we store our customer output in buckets, in S3 buckets, and then move to Glacier as needed. For our DTN forecast system, we also have everything containerized. We run FSX for Lustre and S3. And then again, you'll see common themes in production AI NWP. We're running AWS batch. We are running instances such as GPU-enabled EC2 instances like the G6Es, and we are storing those in S3 as well. Okay, so the first workflow that I'm going to talk to you about is our optimized HPC for specialized modeling. So specialized model, we run 2 of those in-house. They're computational fluid dynamics models, and they are the weather and research and forecasting model, or WRF, and the model for prediction across scales, or MPAS. We run these predominantly for utility customers who are trying to mitigate their wildfire risk and have to make decisions that affect their customers, like public safety power shutoffs. So this has a big implication not only on their business, but on the livelihood of their customers. So here's an idea of a workflow that we have within HPC. This is for our WRF modeling. Everything lives in a single AWS region and a VPC. We have a NAT gateway and a public subnet that handles the egress. And then within a private subnet, we have ParallelCluster handling our HPC 6 and 7A jobs. We use FSX for Lustre here, as I said, and then we store all of our data in our client-specific buckets. And so over the years, we have done some work with AWS in order to optimize our price for performance, especially for these customized models. And one of the biggest successes that we had was working with the AWS experts for HPC and using a test case for Category 4 Hurricane Laura back in 2022. So we tested scaling for MPAS, that model I was just talking about, for a simulation of Hurricane Laura. We used a 15-kilometer global mesh, so covering the entire world, and then a refined grid at 3 kilometers over the Gulf of Mexico. We ran all kinds of tests where we scaled up from 32 to 128 instances. And we found that the sweet spot for price per performance was 64 instances. This really taught us a lesson on how we can scale for other workflows and how we can apply these learnings for the workflows that we do here at DTN. So next, moving on to applying our learnings, like I just said, to our global forecast system. So the DTN forecast system is not just a single weather model. It's an intelligent blend of advanced models from global and regional agencies across the globe. We combine these models along with our proprietary models that we run in-house, such as those specialized custom models, as well as the AI NWP models that we'll talk about in a few minutes. Our DTN forecast system runs hourly out to 15 days. It's a marine and atmospheric coupled model, and we produce over 350 parameters every single day. This decision grade data is then sent to not only our customers, but our downstream applications at DTN that create solutions for sectors like agriculture, utilities, aviation, offshore, and much more. So if we just want to take a look under the hood at the HPC that's driving the DTN forecast system, every single hour we run this forecast model. We take the latest available atmospheric and marine model input and blend it into our model. We compute statistics such as model bias, variance, to understand the skill of that model over the past month. We then apply model weighting using unsupervised machine learning to pick the models that are performing best at each grid cell for each parameter and each hour of lead time. So we're truly getting the best available forecast. Then we apply observation ramping for the first couple of hours of the forecast because we want to take in, again, the best, most recent available data that we have possible. Finally, we would go to the post-processing and derivation step. So this makes sure that all of our parameters, post-blending, post-statistical processing, are consistent and physically reasonable. We then create probabilistic outputs that uses that data here, and that's how we get our decision grade data that is sent to our customers every hour. So this is a tremendous amount of data. It's a high-powered workflow that we have to run, again, like I said, every single hour. And so this poses a challenge if we didn't have AWS and we had the elastic computing that allows us to scale up and work efficiently. Every single hour we run this forecast. It takes about 25 minutes to run a 15-day hourly global forecast to completion. Every single day we generate over 20 terabytes of data, which is a huge amount of forecast data. That's 20,000 gridded global files that are generated every day. And to accomplish this, we run over 20,000 lambdas. And just for the marine modeling alone, I know I talk about the atmospheric side a little bit more because that's my specialty. The marine modeling alone consumes 1,000 cores running on HPC 6A and 7A and produces over 300 gigabytes of data just in itself. So I know some of the buzzwords this year have been AI and how it fits into every sector of technology. And really numerical weather prediction is no different. We are now looking to enhance and improve our models using AI wherever we can. And the AI revolution in numerical weather prediction is truly here. This has really been driven by big tech, startups, and everyone in the industry coming together to see what we can do to improve the weather forecasting across the globe. These numerical weather prediction models are trained on over 50 years of data. So we use reanalysis data from different centers around the world, like the ECMWF or the European Center for Mid-Range Weather Forecasting. And we train those models to get an accurate representation of the atmosphere in the forecast. These AI models are not only trained on decades of data, but they are run at orders of magnitude lower compute costs. The AI models, as you can see in this plot on the left, actually show a clear step function jump in skill compared to its traditional physics-based counterpart. The solid lines here are the 500 millibar geopotential height skill from the ECMWF, which is kind of the gold standard of weather prediction. And then you can see around 2022, there's a dashed line with the corresponding colors that represent the skill in the ECMWF's AI model skill for the same parameter. So you can see that not only is it fast, it's efficient, but it's improving in skill as well. So with that being said, we do run now in production an AI NWP model on AWS. We run a model called ForecastNet, which was developed by NVIDIA. It's got a 1/4 degree global resolution, and it's trained on that European reanalysis version 5. So we run this in AWS, and it's fast and it's efficient, and we run it for less than $9 a day. We run this, and it's less than the cost of 2 coffees. Or if you were making a huge mistake like I did and got a latte from Starbucks here, it's less than 1 latte. So this lower compute cost allows for rapid testing and innovation within our AI NWP models. And like I said, it runs fast. A deterministic model finishes in less than 10 minutes, and then we run a 30-member ensemble. So that's essentially 30 different forecasts, and that compute time is only 15 minutes. So we've been working on this closely with our colleagues at AWS and NVIDIA. We just recently published a blog post with AWS about how DTN accelerates operational NWP using NVIDIA Earth 2 on AWS, and this is a schematic of our workflow. So just giving you an idea of how this works, essentially we break it down into 3 steps. We have data prep, so AWS Lambda functions will trigger that Python utilities container to format the initial conditions, which are the, I guess what you call the base state conditions that kick off the model run. And then we run model inference. AWS Batch deploys NVIDIA Earth to Studio on GPU-enabled EC2 instances, so in our case, those G6Es, to execute the ForecastNet model inference. And then finally, we get to the results, which is what everybody's looking for. So the Python utilities container post-processes the output to quantify the forecast uncertainty and to provide the latest weather data. And this information then goes into our DTN forecast system blend. So just a success story I wanted to share about how we are running these AI NWP models in production on HPC. This was a forecast for Hurricane Melissa earlier in October. This hurricane was very strong, hit the island of Jamaica, unfortunately caused very much destruction of life and property. But I wanted to highlight that this AI NWP model that we are running showed a huge amount of promise in terms of the skill that it provided for this forecast. So this image on the right was a forecast 3 days in advance, and it nearly nailed the point of landfall and then the area of the strongest sustained winds. And one thing that I do want to point out, that even though I'm saying, the skill is really good for these models, we're still finding ways that they can be improved. So for instance, with hurricanes, AI NWP models tend to underdo the intensity. And so we know that it's a known bias. And so we want to make sure that we are using these tools in addition to our physics-based models to get the best information out there. And because of the elasticity and efficiencies available in HPC and AWS, we're able to do that. So this is the same model runs for the same forecast, except here we're running our ensemble. So we have a 30-member ensemble. And what was really neat here, again, this ran in less than 15 minutes. This 30-member ensemble, you can see that there is skill in it. The ensemble lines are converging, which means there's more certainty within the forecast. And it really showed the correct track of the hurricane over the island of Jamaica. And it even showed that sharp right turn that it made just as it was nearing landfall. So again, you want to take these models with a grain of salt. They are really powerful, they are fast, and we can really only run them because of our resources that we have with AWS HPC. And then we can combine them, like I said, with our physical models. So just going on to what's next for us, I've shown you where we were, where we are, and now where we're going. As I mentioned, we're looking into AWS Parallel Computing Service. This is really going to be able to be applied to most of our current workflows that we have right now. It's going to allow us to transition off of that ParallelCluster system that we're using to the next gen fully managed AWS platforms. We're going to move into more advanced AI NWP. Right now we're just running an AI NWP model, but our next step is to actually train one. And we're only going to be able to do that using the high-powered GPU instances from AWS. And then finally, we want to add value-added customer models to our suite. We want to leverage our DTN customer data with pre-trained models and be able to apply them to our customers who have very niche use cases like utilities, fuels, and wildfire. All right, I want to thank you all for coming to this session. I know you had a lot of other simultaneous sessions going on, so I appreciate your time and attention, and I'll hand it back.
Thank you, Taylor.
Thank you.
Fascinating. Well, everybody, I think we're in the final stretch. I wanted to do a quick recap. So today, during this session, we talked about the market trends in HPC. You see a lot of growth, continuing to consume a lot of infrastructure, innovate on the services offered. Cloud adoption is growing faster than on-premise growth, and that's not a surprise for all the reasons that we covered in this talk. AWS is continuing to build optimized HPC building blocks, but also general purpose building blocks. So the set of options that you're going to have in 26 and the years following are going to continue to grow. We had a few cross-industry use cases that I covered really quickly, but then the amazing presentations from Karima and Taylor here talking about ARM and DTN's journey on AWS. Hopefully inspiring for some of you, hopefully some ideas. And look, everything is a journey. You have so many options that you want to go and engage with AWS specialists. We're here to help. I did want to bring up couple additional items that were just announced but didn't really have a lot of coverage. One is we continue to invest, but we continue to invest thinking about all the customers that we don't always take care of. This was announced a few days ago. We are making a $50 billion investment, and I know it's 15 billion, but it's over 10 years, so it's a bit less per year, to go and build AI and supercomputing infrastructure for US government agencies. And for countries or agencies outside the US, if we are able to build this for the US agency, you can only imagine that we'd be able to do the same around the world. That was really important for me to mention because it didn't get a lot of coverage. And the second thing is that in St. Louis 2 weeks ago, AWS received for the 8th year in a row the award for Best HPC Cloud Platform. So I know it's a bit of brag, but I didn't want to put that as the last slide. It is an independent survey that is run by HPC Wire, the authority in HPC and AI publications. And this is the 8th year. We're continuing to improve. We're continuing to add value. Because of all of you customers on AWS, we get better every year. So with that, remember I told you you're going to have QR codes. This QR code will point you to additional HPC sessions. If you like this session, by the way, fill out the survey in the app. Provide feedback. We get better every year thanks to all the feedback. And I just want to close saying thank you to all of you that showed up today for this presentation. Special thanks to Karima and Taylor for joining me on stage. Enjoy the rest of the reInvent this year, and hopefully we'll see you again next year.